Hello, I welcome you all in this presentation related to the subject joining technologies for the metals. In this presentation, I will be talking about the resistance welding processes. So, as the name suggests that the resistance, electrical resistance plays a big role in these processes. Why? Because the welding in these processes is mainly weld joint in these processes is mainly produced by the heat generated due to electrical resistance heating. So, the contact resistance between the wing surfaces plays a big role in these resistance welding processes. Resistance welding processes are basically group of the processes. In all those processes the electrical resistance heating is involved for developing the weld joint, and these are commonly known as spot welding, projection welding, seam welding, flash butt welding, stud welding, and then there is a high frequency resistance welding and high frequency induction welding. In all these processes, the electrical resistance heating is used in one or other way. We will see that in some of the processes even arc also comes into the picture, but they have been placed under the category of the spot resistance welding processes. All these most of these processes are like say the spot welding, seam welding and the projection welding. These processes are commonly used for joining the thin sheets. So, like in automotive applications or electronic components, wherever very small components or thin sheets are to be welded, we will see that the resistance welding plays a big role. For example, in one typical car about 4 to 5,000 spot welds are made. So, it is such a large volume of the spots which are needed to join the different members in a typical automotive car, and mostly these are used for joining the thin sheets. So, in which way the joint is developed, what is the underlying principle in development of the joint using the resistance welding processes. Say in this case we take two sheets to be joined, mostly they are kept in lap joint configuration like this, and so they will be contacting, there will be one contact interface like this. So, if we see the magnified view of the contact interface, there the contact is through the peaks and valleys present on both the sides, and then during the welding the electrodes are brought in contact with the surfaces like this. Of course, these need to be aligned, and these electrodes will be delivering the required current and pressure. These are the two purposes of applying using the electrode. So, the very heavy current is allowed to flow through these electrode into the workpiece. So, it may be in thousands of ampere, like 30,000, 40,000 amperes. So, heavy flow of current takes place through these electrodes, and then pressure is applied. So, pressure helps in bringing the fang surfaces together. So, contact is made firm with both contact of the electrode with the workpiece surface at location 1 and location 2. Since the heavy current is flowing, so the loose contact may result in sparking or arcing between the surface of the workpiece and the electrode, which will damage to both surface of the workpiece as well as to the electrode. So, the firm contact is required first between the electrode and the workpiece, and then of course, the firm contact is also required at the fang surfaces between the workpieces, and that is why sufficient pressure must be applied. So, the pressure is one of the important variable related with the process, because it ensures the firm metallic contact between the electrode and workpiece and between the fang surfaces of the workpiece. And the second is, it helps in consolidation of the in case of the heating, whatever nugget is formed at the interface, it will solidify under the pressure. So, consolidation and nugget formation after the cooling. At the same time, it also prevents any expulsion of the metal being produced due to the electrical resistance heating. Current, I have said, current definitely very high level of the current is supplied, so that the required heat is generated. Current is in thousands of the ampere, and then time, how long that current will be flowing, may be from the milliseconds to few seconds, and so the heat generated in this case will be the function of heat at the interface is most important. Heat will be generated at the contact between the electrode and workpiece also. So, at the contact point 1 and 2 and 3, heat will be generated at all these 3 locations due to the contact resistance, but the maximum contact resistance is observed at location 3. So, it will generate maximum heat under the identical conditions of the pressure and the current which will be flowing. So, the heat generated is obtained through the I square R T, where current is in ampere, R is in ohms, contact resistance, and T is the time in seconds, which will be giving us the amount of the heat being generated. So, the heat generation is less at this point, at the point 1 and 2, and the maximum heat is there at the interface, and because of this, if we try to see the temperature variation at this point and at the contact interface, and as well as the interface between the surface between at the fang surfaces. So, here we will see the temperature will increase and it will go like this, thereafter again it will increase, reach to the peak value, then it will start coming down, then it will be somewhere here, then again it will start coming down. So, some peak is observed at the contact interfaces. This temperature corresponds to the temperature at the both the electrode and the workpiece surfaces, and the maximum temperature is generated. So, this you can say this is the distance from the fang surfaces, this is on the electrode side and this is on the another electrode side, and maximum temperature is of course generated at the fang surface, the contact surfaces of the workpiece. So, here because of the maximum current and the heat generation, because R value at the contact interface is maximum. So, it results in the maximum heat, and this in turn causes this heat results in the softening as well as sometimes even partial or little melting also takes place, and after this melting, what we will see that the solidification will result in the formation of the joint. So, this portion if we see in magnified form like this. So, this is the fused portion which will solidify, and this solidification takes place through these columnar grains. Normally and here we will see that the equiaxed grain structure is formed. So, that this diameter of the melted portion and after the solidification result in as a in form of the weld metal, which is called nugget, and this dimension is termed as the nugget diameter, and this significantly determines the load carrying capacity of the weld joint. So, if we see in this configuration, in this kind of the joint, if the nugget size is small, the load carrying capacity of this joint will be lesser as compared to the case when the joint means nugget diameter is large. Larger nugget diameter in general increase the load carrying capacity or the shear area multiplied by, of course, shear strength will give us in this lap joint configuration the load carrying capacity under the shear conditions. So, increase in diameter of the nugget directly determines the load carrying capacity, and the size of the diameter nugget diameter is governed by the amount of heat being generated. So, we need to see what are the parameters that affect the heat or the individual effect of the welding parameters on the heat being generated. So, as far as that effect is concerned, before going into that, let us see the kind of cycle which is followed in resistance welding processes. So, that cycle goes in like this, that as a function of time, how the pressure and current varies. So, here if it is a force which is applied through the electrode and as a function of time. So, initially when the electrodes are far apart from the surface of the workpiece like this, So, the electrodes are far apart, the pressure is 0 and then the pressure is increased as soon as they come in contact with the surface of the workpiece, pressure is increased. So, like this. So, here they are brought in contact, pressure is increased, then pressure is increased gradually, then it is kept constant like this, kept constant, and then slowly it is brought down as a function of time. So, this axis shows the variation in pressure as a function of time, and here as soon this is the portion where squeezing is taking place, and when this squeezing is over, the electrode will be in firm contact with the surface of the workpiece. After this only the flow of the welding current is started. So, once the flow of current is over, heat is generated, melting at the fink surfaces will be taking place. So, this is the time when the current is allowed to flow, known as welding time. First is squeeze time, and here no pressure zone, welding time, and thereafter under pressure it is kept for some time. This is called hold one, in which the melted the nugget which has been formed will be solidifying under the pressure, and thereafter once the solidification is over, the release phase comes in, the pressure is reduced gradually, and then the sheets are taken off, and this is how the cycle is repeated. So, basically squeezing, welding, holding, and then off. This is the kind of cycle which is followed in most of the resistance welding processes like spot welding and projection welding. Now, we will see the kind of requirement or expectation from the electrodes which are being used. So, the heavy current flows through the electrodes, and the pressure is also applied through these electrodes. So, electrodes are supposed to withstand under the conditions of the high temperature. So, this is one requirement, that the electrode material must be must have the high temperature strength. Another is it comes in contact with the surface of the workpiece very frequently. So, repeated contact or repeated relative motion between the surface of workpiece and the electrode causes the wear. So, it must be wear resistance, since heat is generated at the contact interface with the workpiece. So, this heat must be transported away to avoid unnecessary damage to the electrode material. So, the conductivity, like thermal conductivity of the electrode material must be good. So, the K must be high, and to satisfy all these requirements, normally the copper based alloys are used. So, these electrodes are normally water cooled also to maintain the safe temperature limit, but since they have to handle the heavy current, so the good electrical conductivity is needed, high temperature resistance is needed, high thermal conductivity is needed, and good wear resistance is needed. So, the copper is normally alloyed with the various alloying elements like copper chromium and copper tungsten or copper chromium, copper tungsten, chromium, sometimes zirconium is also copper, zirconium, tungsten systems are also used. These alloys offer very good resistance to the thermal softening, good wear resistance without much compromising on the electrical conductivity of the electrode. However, alloying will definitely be reducing the thermal conductivity as well as electrical conductivity, but they provide enough value of these properties so that they can be used effectively for the purpose of developing the joints. Especially in some of the cases, like if the electrode is of particular shape and size, gradually these wear out in course of the operation. So, diameter increases, increase in diameter is actually reduces the current density, and because the current is allowed to flow through the larger area. So, reduced current density results in the reduced heating, and so the nugget diameter sometimes gets reduced. This problem is mainly encountered when we weld the zinc coated steels. So, the zinc coated steels, like the steel sheet having the coating of the zinc, and when it comes in contact, so the copper due to the continuous heating interacts with the zinc, and it forms the brass. So, this brass being hard and brittle and continuous under the adhesive conditions causes the wear of the electrode at much faster rate. So, normally the electrode which can produce the joints of 4000 to 5000 in one go, 4000 to 5000 number of the spots without compromising in the nugget diameter. When the zinc coated steels are spot welded, you may find like 200, the diameter gets modified and it is enlarged to such an extent that it needs the replacement or the refurbishing, so that the same size of the nugget diameter can be achieved. So, significant reduction in the number of spots, number of the welds which can be made, spot welds which can be made in case of the zinc, in case of the zinc coated steel sheets, that is reduced significantly, because the formation of the brass at the electrode surface reduces, increases the wear rate, which in turn reduces the life of the electrode significantly. Now, we will see the effect of the individual parameters, effect of the resistance welding parameters on the joint performance. So, there are three important parameters like current, pressure, and the time for which current is allowed to flow. So, all these factors in fact govern the heat in one way, like I square RT. T is directly proportional to, and the heat generated is in proportional to the square of the current being supplied, and pressure in fact affects the contact resistance. So, now we will see that when the current is increased, the tensile shear load carrying capacity in kilonewton, the tensile shear load carrying capacity in kilonewton increases with the increase in current, and then it starts decreasing after reaching to the maximum. We know that increase in current will increase the heat generation, which in turn will increase the size of the nugget which will be made, and that is good from the shear strength point of view. For low current, nugget size is small, and as the heat generation is increased with the increase of welding current, nugget size will keep on increasing, that in turn will increase the tensile shear load carrying capacity. But after reaching to a particular value, we will see that excessive development of the excessive molten metal due to the too much heat generation, expulsion of the molten metal starts, and in that case strength starts decreasing after reaching to the peak value. Similar kind of the trend is also observed in case of the pressure variation and time pressure variation. So the increase in pressure or the load initially, so of course we need some minimum contact pressure in order to have the good current flow through the workpiece without sparking, and thereafter we will see that initially when the pressure is less, the current will not be flowing without the sparking, so some minimum current is needed. So initially the increase in pressure helps in better consolidation, proper solidification under and thereafter, but too much increase in pressure starts decreasing the tensile tensile shear strength capacity of the nugget or of the joint, and this decrease is attributed to the reduction in contact resistance. Say for if the pressure is too high, then increased metallic intimacy at the fang surfaces will be decreasing the contact resistance. So under identical pressure conditions, the amount of heat being generated will get reduced, and that in turn will reduce the nugget diameter. So but we need to have the reasonably good pressure to avoid the sparking, and use of the too high pressure will reduce the contact resistance, and but little marginal increase in pressure helps in effective consolidation as well as the solidification of the metal at the interface. And similarly, similar to the current, increase in welding time also increases the strength, and thereafter it becomes almost constant. So here the tensile shear strength load carrying capacity of the, so basically the load carrying capacity of the joint increases linearly with the increase in the time for which current is flow. So basically increase in time increases the heat generation, increases the nugget size, and thereby it increases the load carrying capacity of the nuggets. So this is how the welding parameters affect the joint strength, and it is necessary that proper control over the current I and the T is maintained. Once these parameters are obtained, automation of the process is very effective. Once the process, after optimization, once the process is optimized, rate of production is very high in case of the resistance welding processes. There are certain requirements related to the nugget diameter and the electrode diameters which are required for developing the weld joints, like the electrode diameter requirement is like 5 times of the root of the thickness. The T is the thickness of the plate in mm, thickness of a sheet in mm, and the nugget diameter is 6 times of the thickness of the plate. So this is about the requirement side. Now we will see that once the one spot has been formed in spot welding, if the number of spots are to be made for for higher load carrying capacity. So, once the one spot is made here by applying suitable electrode and having the flow of current through this. So, heat will be generated and that nugget will be formed. Once the one nugget is formed, for developing the another nugget, it is required to use the higher level of current, and because since already metallic connection is established between the two plates. So, the current starts flowing through this metallic connection, and because of this the flow of current through from one electrode to the another electrode directly through this one, it gets reduced because already metallic connection exists in. So, current instead of flowing directly from the high contact resistance zone, it starts flowing through the low contact resistance zone, and that is why we require higher level of the welding current. This one is called shunting effect. So, shunting effect means some of the current will be flowing. If some of the spot welds have been made, then some of the current will be flowing through the already developed nuggets, and therefore, the current requirement increases for making the further nuggets in case of the spot welds. To overcome the shunting effect, the magnitude of the current is normally increased. So, this is what happens in case of the spot welds. Similarly, in case of the seam weld, now we will see the seam welds are made in three ways. Seam weld means the continuous, just like with the help, they are made with the help of the rollers, which will be rolling continuously and current will be fed. So, here the seam can be made like this, one spot, another spot, another spot. This is like a tack welds are made, or they can be made in like the overlapping kind of the tacks like this. So, this is overlapping weld, or instead of overlapping, if the weld is made continuously rather than just like intermittent or overlapping weld. So, continuous. So, there are three types of the one is tack weld, overlapping or continuous kind of the seam welds. So, these type of the arrangement is continuous or overlapping type of the seam welds are normally used for making the pressure or leak tight joints of the seats. So, mainly for the tanks and wherever it is required that the joint is leak proof, the seam weld is made. That also works in the same way like contact resistance heating principle. So, now I will summarize this presentation. In this presentation, I have talked about the basic principle of the resistance welding processes, effect of the different parameters, the role of the electrodes, and how the joints can be made effectively using the common resistance spot welding processes. Thank you for your attention.